So at this point in your mathematical career, you've become expert at the magic formula, building a Taylor polynomial or a curvy function to represent another curvy function. So what we're doing is we're now taking that idea and showing you how your AP test writers, your future college professors, anyone who loves math can take that whole concept and devise some really tricky, stealthy questions to see how well you understand that concept. So in the example I show you today, what you have is what I would call informally a derivative value generator. So when you look at something like this, your first instinct is to think that this is a formula that will generate term by term of a series. But read your notation carefully. F to the nth of 3 means the nth derivative evaluated when you plugged in an x value of 3. So as I cycle through my various n values, this thing is going to turn into a number which is going to represent the nth derivative value at 3. And we're saying that that derivative is the derivative of some function g of x. So in other words, for some mysterious function g of x, if I wanted to know g prime of 2, that's the second derivative. And then I can go ahead and plug in a 2 and I get this value. Maybe I should have used g to the n of 3 since I'm using g of x over here. So that's a little bit of a math lawyer oversight. I apologize. So once you realize that this thing is just generating derivative values for you, you could be asked any question that you're used to being asked about these Taylor polynomials. For example, write the first 3 non-zero terms of p of x. Use your polynomial approximation at the second degree to estimate a value of g of 4. And then compute the maximum possible error that you could have had with that estimate, and ... because there's all sorts of questions you could be asked about this situation. I'm going to quickly go through my solutions to these 3 hypothetical questions, and I'm doing them quickly because you really, hopefully, feel comfortable with all of those, so it's a reminder of the fundamentals. So for this first one, write the first 3 non-zero terms. Basically, this derivative generator, this thing right here, is going to be used when I do this to fill out the derivative portion of the magic formula. Remember, the magic formula says that this is the derivative evaluated at the x value in question. And in this case, the value in question is x equals 3. But then this is the n factorial. This is the x minus center, or 3 raised to the n power. So everything you see here is the magic formula. The only thing related to this problem that is new is this derivative value comes from that derivative formula generator. This looks like a big old mess, but if you wanted to simplify it, you can turn this into this. There's no rule that says you have to simplify that, though. You would only do that if you think you needed to make your next steps easier. So now we have our first 3 non-zero terms of p of x. This could be a way that the AP tests your ability to use the magic formula to build a polynomial approximation without you depending upon taking derivatives on your own of a real function. By the way, these are the first 3 non-zero terms because that first term ended up being a 0, but it's kind of a coincidence that it's also a third degree polynomial. Your first 3 non-zero terms doesn't have to end up being a third degree polynomial. The next question is, hey, can you please use your second degree polynomial approximation to estimate a value of x equals 4 of the real function? So now I'm not going to need to use my entire polynomial that I just built. I can stop at the second degree term. So what I get when I do this is this kind of ugly thing. I plug a 4 into there and to there. I don't care about that last term. And I get this, and I don't have any desire to try to simplify that. I'm going to leave it as is, no harm, no foul. Then the last request is this. You know, when you did this approximation, you had some error. What's the maximum possible error that you could have had when you made that approximation? Well, since the approximation was made using this, p of x, and I'm interested in the maximum possible error, I start thinking, okay, it's either an alternating series error bound or it's a Lagrange formula error bound. And since this is an alternating series, I'm going to use that one, which I think most people would say ends up being easier. But of course, I have to show that this is a convergent alternating series. So at x equals 4, I know the series is alternating. I can see that. The absolute value of each future term is less than the previous term. If I plugged in 4s and I did that calculation, that would hold true. And the limit ends up equaling 0. All of these are the conditions that just say, hey, I have a convergent alternating series, so it's okay to do this. So now my maximum possible error is simply going to the next available term. And by the way, our next available term is right there because we've used the second degree to make our estimate. The third degree is the next available term. And I just plug my 4 into that next available term. That's the maximum possible error, or how far off this could possibly be. And our brains can't wrap our head around either of those values, so we just have blind faith. So we did some dipping of our toes into the AP waters, and really the only thing we did is we said, hey, sometimes you're given something that looks like it's generating the terms of the series, but it's actually just generating the derivative values used to build the terms of the series.